Okay, good morning. So we continue the lesson with the limits of functions. So we want to actually improve our skills in calculating limits in this session. So I will start giving you some examples. So example, so determine the following limits. Or if you believe that one of them or some of them do not exist, just mention why, okay? I will start with the very simple examples. So you want to calculate the limit of 3x to the power of 2 plus 5x minus 2 when x goes to negative 1. Yes? So I told you that when x goes to negative 1, it means it is very close to minus 1, but certainly it is not equal to minus 1. But of course, it doesn't matter here in this case. If you want to calculate a limit, first of all, you just put the number inside to see if something is strange going on. For example, you have division by 0 or something like that. In that case, you have a little bit of problem. You have to solve it. We will come to those examples. But you need to understand that when you want to calculate limit, the first thing that you want to do is to put the number inside to see what happens. If nothing happens, that is your answer, okay? For example, in this case, if I put minus 1 here, nothing strange will happen. I will be able to find a number at the end. That number is your limit. This becomes 3 minus 1 to power 2 plus 5 times minus 1 minus 2. And the answer becomes, this is 1, 3. So let me write 3 minus 5 minus 2. So it is minus 4. So the limit is minus 4, as simple as that. Or, for example, if I give you this, the limit of square root of x to the power of 3 plus x plus 3 divided by x to the power of 2 plus 5, and x goes to 2. Okay, so what you do, you just put the number there, because hopefully you realize nothing strange will happen, because if I put 2 here, I don't have any problems. Yes? So just put the number there, so it becomes 2 to the power of 3 plus 2 plus 3, and then divided by 2 to power 2 plus 5. And then you calculate this number. So the denominator is 9, the numerator is 8, 10, 13, yes? And then you have a square root of 13. And of course, you can write it as a square root of 13 if you want to, divided by square root of 9, which is just simply 3. By the way, it is reasonable. I want you to understand, because if you are allowed to put 2 exactly here, what you get is exactly this number. Now, when you are not exactly at 2, you are close to 2, it is clear, hopefully for you, that the values of the function are getting closer and closer to this number. That's not that strange, actually. That's according to what we defined for the limits. But of course, these are boring limits, because that's just polynomials putting numbers there, okay? Interesting things can happen, for example, if we have this situation. So number 3, we want to calculate the limit of 2x squared minus 50, for example, divided by 5 plus x, when x goes to negative 5. So for example, you want to calculate such a limit. Again, you don't know what's going to happen. You try to put minus 5 there, and then immediately realize that you have a problem because then the denominator vanishes. Yes? In this case, actually, technically it is it's the previous lesson. You need to be able to factorize, simplify, and things like that. So this is why we spend a lot of time learning them. So if you want to solve this, you need to factorize and simplify this expression. Okay, for the denominator, I cannot do anything, and this is important now. If you are doing some simplifications, you are not allowed to just drop this. You have to copy and paste. You shouldn't be lazy. Be careful about that. So you need to write x limit x goes to minus 5, and then you will start working on this part. For the denominator, of course, you cannot do anything here. What is your suggestion for the numerator? The point is to factorize and simplify, okay? So between these two, I can factor a 2 out. So I factor a 2 out, and then it becomes x squared minus 25. Okay, still it is not enough. I have to continue, but hopefully this is very simple for you by now. This is just a conjugate pattern, so this becomes the limit 2, and I factorize it, x minus 5, x plus 5, and then divided by 5 plus x. And by the way, you see that still I am keeping this symbol x goes to minus 5. You have to write this down. But you see that 5 plus x and x plus 5 are exactly the same. Can I simplify them? Of course, in the previous lesson, we didn't care about this, we just simplified. But here, I want you to understand it a little bit better, because x goes to minus 5, it means that x is very close to minus 5, but it is guaranteed not to be minus 5. And when x is not minus 5, so 5 plus x is definitely not 0. So we are really on the safe side if we divide the numerator and the denominator by this factor. I'm just describing this because I want you to understand. You don't need to explain it in the exam, okay? I want you to understand that this is important. And then you need to know, again, I am putting this limit sign. I am left with 2x minus 5, and I have x going to minus 5. So you see that I have written this limit sign all the way up to here, but now everything is okay. I can take x and put minus 5. At the very last step, I have to drop the limit sign. So this becomes 2 minus 5 minus 5. And the answer becomes minus 20. Okay? Yeah.
If you just put minus 5 in the beginning, right, doesn't that just become 50 minus 50 over 5 minus 5?
Yes, it becomes 0 over 0.
Yeah, but how can what?
That's exactly the point, because you cannot put minus 5. That is exactly, let me just repeat it again. When you say x is minus 5, so you need to understand that x is not minus 5, because if x is exactly minus 5, the numerator becomes 0 and the denominator becomes 0. So this means x is not minus 5. If I give you this and I ask you, I will come to you, and I ask you to calculate this for minus 5, you should say it is not possible or it is not defined for minus 5. So be careful. Let me just repeat this again. If I give you f of x equals to exactly the same function, and in the exam I ask you calculate f of minus 5, I want you to understand the answer that you should provide. First of all, I am not allowed to ask this question. Why? Because minus 5 is not in the domain. But it's still, if I am careless and I ask you this question, you should say it is undefined. But this is not the situation here. The answer is minus 20. So this is exactly what I want you to understand. There is a big difference between calculating the value of the function as a number by calculating its limit. There it is not defined, but here you see that the function is minus, the limit is minus 20. The reason is that You are right. This is 0 over 0 if x is minus 5. X is not minus 5. It is very close to minus 5. So the numerator is not is not 0. It's very close to 0. By the way, when a number is very close to 0, this is the terminology we use. We call it infinitesimal. Okay, or a negligible number. So if x is exactly minus 5, the denominator is exactly 0. But x is not exactly minus 5, it is close to minus 5. So the denominator is an infinitesimal. For the same reason, if I put minus 5 exactly, it becomes 0 exactly, but x is not equal to minus 5 exactly, so that's also an infinitesimal, yes? Yes?
But in the previous examples,
Yeah.
when you put in like what the limits we're supposed to approach to, like minus 1 and 2, it becomes a number. You say that that is the limit. Like the limit is minus 4 or squared.
Yeah, in that case, it coincides with the value of the function.
But what is the reason that you wouldn't say that this limit is undefined? Because when it's
No, because I told you that when I see this, it means x is not minus 5. If I give you f of minus 4.999, this is not undefined. So still you can take x and put this number in. You get a value. Yes? So that's the point. It means that here, so this, I told you that if you want to understand that, it means that you have to be patient, because the limit is not a number, is a process. So it means that I have to put x and my f of x here and start writing the numbers close to minus 1, and then calculate the value of this function for the numbers close to minus 1 and see what is the behavior of my function. If the values are approaching to a particular number, that number is called the limit. And it doesn't mean that I am really achieving that value or not. Yes? Did I answer your question? Yeah?
So this original function, you've simplified it down to 2x minus 1, right? So, but they're not entirely equal for them.
No, they are entirely equal when x is not minus 5.
Yeah, exactly. But then what would you say?
No, that's exactly what I'm saying. 2x squared minus 50 divided by 5 plus x is exactly equal to 2 times x minus 5 if I respect the fact that x is not minus 5, which in this case is true because of this.
Yeah, but how would you specify that?
What do you mean?
Well, for example, if you were to just simplify this and not think about it, and then just use 2x minus 5 and then you minus 10, and then you might have the idea that you could use minus 5, but you obviously can't, because in the original equation.
No, I told you, you have to test.
Yeah.
If you put minus 5, you are in trouble. It is 0 over 0. But you shouldn't be disturbed at this point, because 0 over 0 is happening if x is exactly minus 5. Yes? If it was that problem, that was the end of the story. Just right now, you just say f minus 5 is not defined. But for the limit, still we have a chance that the limit still exists even if f of minus 5 does not exist. Okay? And then under that condition, I am doing the rest of the calculation. Yes?
I suppose what just confused me is because you say that those two are like exactly equal, but when you put in the same number, you get different answers. Like in the first one, you get 0 divided by 0, but in the second one, you get minus 20.
No, I told you again, this function is exactly equal to this function if you don't put x equals to minus 5. Yes? Here, so the notion of limit is a little bit complicated, but so what I'm saying is that, let me make it a simpler example, okay? So if you have x squared minus 1 over x minus 1, okay? X goes to 1. And then I have a function f of x is equal to x squared minus 1 over x minus 1. In this example, if I ask you what is f of 1, you just simply write undefined. Yes? How did I understand? Because when I put 1, the denominator becomes 0. Yes? But when I ask you to calculate this limit, this is the method that I am telling you do it. It doesn't mean put x equals to 1. Yes? This means that you need to write x and try to get the values of x which are close to 1. For example, we have to decide which side we want to approach. For example, let us approach to 1 from the right-hand side. So I would write with 2 here. So let me just write here. Let me go from a smaller value, 0. And then if I put 0 here, I don't have any problems. When I put 0 in the function, not here, in the function, it becomes 1. Let me increase the value of x a little bit. I put 0.5. You have to be patient. Take 0.5 and put it here, and then calculate it. You get 1.5. And then you go a little bit further. And then you put this number here. Be patient. Calculate it. You get 1.8. You put 0.9, and then be patient. Put it there. You get 1.9. And then if you increase, even getting closer, you get something like this. When I write, so this table is what you need to understand for limits. That table is summarized in saying that the limit of this is 2. Yes? So instead of writing something like this, we just simply write this. And now you understand that when I am getting closer to 0, I am not allowed to stand exactly on 1. So whatever I have done is completely valid. Then you need to understand, is it the case that these numbers are stabilizing around the point? If that is the case, that number is your limit. Yes? So this is when you write something like this, you need to imagine this is the behavior. Okay, then you need to think in this way. Every time you want to think in this way, or you want to learn the tricks and techniques to calculate the limits. Of course, both of them are important. But I want you to understand the way that for example, if I want to do this calculation, I put 1 here, I see that I am in trouble. Then I factorize the numerator, and the denominator is the same. And now, so far, I hope that you agree that this is exactly the same expression, yes? But now I am telling you I can simplify these two because x is very close to 1 but not equal to 1. So x minus 1 is not only a common factor, but this is not 0. When it is not 0, I simplify that, so the answer becomes the limit of x plus 1. Because what I am saying is this. I have two functions. One function is this, another function is this. If I ask you, is f of x equals to g of x, what is the answer? Is f of x, this function, equal to this function? The answer is definitely no, okay? So mathematics is actually unforgivable. You just say yes or no. Is f of x equals to g of x? The answer is no, okay? Because of the problem that happens at x equals to 1. At x equals to 1, this is undefined, but I don't have any problems here, that is 2. So this is false, okay? What I am claiming the limit of f of x when x goes to 1 is equal to the limit of g of x when x equals to 1. This is true. This is what I'm claiming. So the functions are not equal, but the limits are the same. And that is clear. Why? Because the only problem that happens is when x is equal to 1. If x is not equal to 1, the values of the function g and the values of the function f are identical. So if this is getting close to a number, the values of x also getting close to the same number if x is not equal to 1. Is that clear? So it means let us try to check. It means that if I have another row for g, so remember f is that function, g is the other function. If I have another row for g, if I put 0 for x in g, what do I get? I get 1. If I put 0.5, what do I get? 1.5. If I put, I don't know, 0.8, I will get this, I will get this, I will get this. So you see that the values of f and g are identical if x is not equal to 1. So this means that even though the function f is not equal to function g, but if I respect the fact that x is not equal to 1, whatever I get for f, I will get the same for g. Is that clear? So it means that the functions are not equal, but the limits are equal. I don't know, is that understandable? Yes or no? Yeah? Okay, so that's the idea. Every time, of course, it is not bad to think about this all the time, but then after a while, even if you don't care about this, this is the technique to calculate it. But of course, I understand that just calculating without understanding is useless. Yes, is that clear? Yes or no? Okay. So don't think that we have a double policy here. That's not a double policy, yes? You say that, okay, we cannot put it here, but so what happens that at the end you put it there, yes? I want you to understand that's a not double policy. Probably the most precise way is to define two functions, one f, for example, one g. I am not claiming that the function f is equal to g, but I am claiming that the limit of f when x goes to 1 is equal to the limit of g when x goes to 1. Why? Because when I get closer and closer to 1, but not 1, the values of f and g are identical. So if the value of this is approaching to 2, the values of g also approach to the same value too. Okay, is that understandable? Yes or no? Yeah? Okay. Yeah, it's good to think about this, but this is the trick. Okay, so this is, by the way, that is very interesting. This number in the numerator, for example, let me call here. When I put 1 here, you might say this is 0 over 0, but this is not the fact. This is an infinitesimal number divided by an infinitesimal number. Okay, because if x is exactly 1, the denominator is exactly 0. But x is not exactly 1, it is very close to 1. So the denominator is not exactly 0, it's a very small number. A very small number in mathematics, we call it infinitesimal. And the numerator is also infinitesimal. Okay, and that is something that I want you to understand. This infinitesimal divided by infinitesimal is called undeterminate form. Why is that? It is clear, even from these two examples. Because here I have a negligible number divided by a negligible number, but the value of the limit is 2. Here I have the same thing, a very small number divided by a very small number, but the value turns out to be minus 20. So this is called undeterminate form because you cannot answer the value unless you do the calculation. Every kind of numbers is possible for infinitesimal divided by infinitesimal. Yes? So if you divide a very small number by a very small number, the answer depends to the behavior of the function that you are studying. Okay? Because why this is important? Because any number divided by a number itself is 1. Okay, this is the reason that I want you to understand that every number divided by itself, if that number is not 0, is 1. Okay, you might think that then when the numerator is infinitesimal and the denominator is also infinitesimal, you might think that the limit would be around 1 all the time. But this is not the case. It really depends to the behavior of the function that you are studying. Sometimes the answer is minus 20, sometimes the answer is 2. It is undeterminate form, so you have to do the calculations, yes.
Can you like define an infinitesimal? Is it like a number we know, which is like this is an infinitesimal?
No. Infinitesimal means its limit is 0. Yeah, something like this. No, okay. If the limit of a function is 0 at a point, we say that that value is infinitesimal. So you can consider this. Okay. I hope that at least you understand, because this is the reason that the book doesn't discuss about these things at all, because they are complicated. The reason that they bring the limit, because you want to calculate the derivative next lesson, in the next chapter, you have to know how to calculate limits. But that is actually good, and then you will feel the power of limits. By the way, from historical point of view, Newton didn't know about limits. He invented this to calculate the rate of change, okay, the derivative. That was important. The notion of limits was actually formulated. It was a hard concept for mathematicians to grasp. Actually, I think Cauchy, French mathematician, was actually, I think, in the beginning of 20th century, gave a final definition of the notion of limits. Okay, even though people were working with the notion of limit, it was not that rigorously defined. Okay? But the idea is exactly the same. It is not that complicated. Okay. So the last line is that those functions are not equal. I am not claiming the functions are equal, but I was claiming the limits of those functions are equal. So instead of calculating the limit of that function, I calculated the limit of the other function. Yes? Okay. So let us go to the next example. So for example, I want to calculate the limit. So this is number 4. So you can consider that number 4, that one actually. I calculated that or didn't. Okay, so let me just write number 4 here. So f of x, let me calculate this. Limit of x goes to 1. I have x squared minus 1, and I have x to the power of 2 minus 3x minus 4. So let me think a little bit. No, let me make it positive 3. Yes. Okay, again, you put 1 here. What you face, in the numerator you face 0. That's not a big problem. If the denominator is not 0, then the answer is 0. For example, assume that this is just 2. And when x goes to 1, what happens? The numerator becomes 0. The denominator becomes minus 1. 0 over minus 1 is just simply 0. The problem happens if the denominator becomes 0. Okay, so this is the case. If I put 1, the numerator becomes 0, the denominator becomes 0. By the way, this is a sloppy language. If I am not allowed to put x equal to 1. If x is 1, the numerator is 0. X is very close to 1, the numerator is a very small number, but not 0. And when I put 1, the denominator becomes exactly 0, but I'm not allowed to put x equal to 1. X is very close to 1, so the denominator is also a very negligible number. So I am dividing a very negligible number by another negligible number, and I want to see what will be the value of this limit when I am around 1, very close to 1. Yes? Okay, so what should I do? That's how to calculate it is simple. It's just a trick how to simplify this function. So what I do, I will try to factorize that. So the denominator, factorizing the denominator is simple. So it is x minus 1, x plus 1. For the numerator, I hope that you have enough experience. This is one of the famous trinomials. So you need to write one x here, another x there. And then you would say that, okay, I need two numbers whose sum is plus 3, and then the product is negative 4. So what is that? So it's one of them is positive 4, the other one is negative 1. And then x goes to 1. Okay, let us review this again. Am I allowed to simplify these two? Yes, because x is very close to 1. First of all, x minus 1 is a common factor because we can only simplify common factors. This is on the one hand. On the other hand, when x is very close to 1 but not equal to 1, x minus 1 is a very negligible number. It's not equal to 0. So I'm on the safe side if I simplify it. But now another thing that happened there. I want you to understand it's not a circular argument. This is crucial to understand. I wanted to put 1 here, it didn't work, then I simplified that, I put 1 back again here. If you want to understand it rigorously, it means that you are facing two different functions. That function and that function are not equal functions. But if x is close to 1 but not equal to 1, for those values, the value of this function and the value of this function match. Yes, if x is not equal to 1. Yes?
If we're outside of limits, like if we're just calculating this normally like you would any equation, could you not do this then?
No.
Yeah.
No, you cannot do that, yes. Unless you emphasize that I am doing the calculation when x is not equal to 1. Yes. So by the way, for this function to match with this function, you don't need to be close to 1. The only thing is that x shouldn't be 1. Okay? So if x is not 1, it is guaranteed that this function, and so the values of the function match with the values of this function for the corresponding values. Yes? Minus 1 is also. Minus 1 is a different story. Because for minus 1, the numerator is not 0, but the denominator is 0. We will also discuss a little bit about that. That is that the limit becomes infinity. We will discuss about that, but let us do it step by step. Okay, now can I put 1 here, there at the end, or no? So what is the limit of that function? Just put 5 there, the 1 there. It becomes 5 over 2. That's the limit. So you see that all these functions that I have written on the board, these three, have 3 different values for the limit, but all of them are of the same type. They are negligible number divided by a negligible number. And when you are simply taking this, you are saying that I am lifting indeterminacy. So x minus 1 was the factor causing this indeterminacy, because x minus 1 was the culprit here to make the numerator and the denominator 0. When you take it out, then you will not face any problems. So this means that I lifted the indeterminacy. I took away the indeterminacy, the factor causing indeterminacy. Okay, but don't make it so hard for yourself. This is the limit, yes.
Wait, what did you say before? Did you say that those two equations are those two functions, like are they equal?
No.
So if you put in a number in both of them, it wouldn't give the same answer.
No. This function, if someone writes this, someone writes this, I would say it's false. That's because so these two are not equal unless x is not 1 or minus 1. If x is not 1 and minus 1, this makes sense, that makes sense, and the values are always the same.
So if you would write that one first and then write like unless x is not equal plus or minus 1, then it would be true.
So that's the problem. In the previous lesson, if you write this, that's okay for me. But even in that lesson, if you watch the videos, I emphasize that on the condition that this is not 0, I can simplify that, which is always implicit in these questions. To be honest, if I want to show this, so for example, if it is the previous lesson, I am not, if I just say show the equality, this is a wrong statement. Okay? I should say that if x is not 1 or minus 1, show that this is equal to that. But in the previous lesson, we just, I don't know, this is common. We don't say that. We just say prove this. Okay? But it means that whenever you want to prove the equality, these two should make sense and then make them equal. If they are nonsense things, they have to say that nonsense is equal to nonsense. Yes? That's not possible. Okay. Okay, so now let me, so you know how to do these things, and then one thing that will be important for us is this question. Containing square roots. For example, I want to calculate the limit of 3 minus a square root of x over x minus 9. So let me write it simple first. Square root of x minus 3 over x minus 9, x goes to 9. Okay, we want to actually calculate this. So what is the problem here? The first thing that you have to do is to see what happens if I put 9. But the denominator vanishes. When the denominator vanishes, there are two possibilities. Either the limit does not exist at all, or it is of that undeterminate form. By the way, undeterminate is wrong. Indeterminate, yes. I don't know why I wrote undeterminate. So that indeterminate form is happening. So do you think it is impossible or that is indeterminate form in this case? So you put 9 in the denominator, it vanishes. So it means that you are facing a problem, yes? And then you calculate, you put 9 in the numerator as well, that also vanishes. Okay? What vanishes here it means that you are very close to 0, but not exactly equal to 0, because x is not exactly equal to 9. So the numerator is an infinitesimal number. The denominator is also an infinitesimal number. So I told you that when you have infinitesimal and you divide it by another infinitesimal, this is indeterminate. And then you have to lift the indeterminacy. But the ones that include third sign are different from these tricks. So that's a new technique that you need to learn. What happens if I want to calculate this limit?
Factorize the denominator to x squared.
Yeah, that's correct. But this is, I don't want to do that. If you write this, that's completely okay. But my preference is to use conjugate rule, because if this is a little bit more complicated, might be you are lost how to do that.
Well,
Okay.
I make use of the conjugate.
Yes, that's, yeah, but you said conjugate factorize that. What I'm saying is to multiply. Okay, this is the one that I want you to do. I want to get rid of the third sign. I multiply the numerator by the one which makes a conjugate pattern, but I cannot just take the problem and change it unless I divide it by the same thing. Yes? So this is the trick I want you to learn, because if this is a little bit more complicated, then this is the trick will work. So we have two tricks in calculating these kinds of limits. One is factorization that you learned before, and one that you just learn now. Okay? And then what happens if you multiply these? I just juxtapose them, I just put them aside. So x minus 9 square root of x plus 3. But in the numerator, when I multiply this by that, I intentionally made it in a way it makes a conjugate pattern for me. So what will be the answer? It becomes the first one to the power of 2 minus the second one to power 2. X goes to 9. Yes? And then what happens? That x minus 9 that appears and that x minus 9 are cancelled now. Am I allowed to cancel it? Yes, because x is not equal to 9, even though it is very close to 9. But when I calculate it, don't be lazy to respect to writing properly. So the numerator, what is left is 1. In the denominator, what is left is this guy. And x goes to 9. Okay, again the same story. I am not claiming this function is equal to this function. Yes, they are equal if x is not equal to 9, which is valid because x is not equal to 9. If x is not equal to 9, I am on the safe side to say this is equal to this. If this is equal to this, of course, the limit is also equal to the limit of this. That's another way to rephrase it. Okay, so what can I write? I put 9 here, and I don't have any problem. So this becomes this. Square root of 9 is 3. So the answer is 1 over 6. Yes?
So you said about like infinite limits. Is it when you have a non-infinitesimally small number divided by an infinitesimal number? It becomes
Yes.
infinite.
Yeah. Yes?
Can you give an example of how an equation would look if the limit doesn't exist or isn't defined?
No, first we had this before.
Yeah, but just because
No, we had this before. When was it? We solved a lot of problems with diagrams.
right, but just
The left limit and the right limit does not exist.
Like if we try to numerically solve like limit of 1 over x.
Yeah, exactly. Because the reason that I don't want to take, because you have still trouble here. I don't want to confuse you with a new concept. But if you want, yes, the limit of 1 over x when x goes to 0 does not exist. Because there is no number. So what is the meaning of this? It means that, so let me write x from the right-hand side, okay? So what does this mean? It means that if I write x and I want to write 1 over x, I have to get closer and closer to 0, okay? And to see what is the behavior of this function. For example, let me choose 1 for x. Then the value becomes 1. Now let me make x a little bit smaller, getting closer to 0. For example, let me put 0.5. I am making myself closer and closer to 0, and I want to investigate the values of the function that appears. So what happens if this is 0.5? It is 2. Okay? And now let me make it even smaller, 0.1. What's the value? 10. Let me make it smaller, 0.01. What's the value? 100. So if I make this smaller and smaller, what is happening? So yeah, for example, let me take this. So then what do I get?
100,000.
The 100,000. Okay? So you see, by making x smaller and smaller, there is no particular value, so that values of 1 over x are stabilizing around that. They're actually increasing and increasing without any bounds, yes? Is that understandable? This is not, by the way, hard. I am making x smaller and smaller. I am putting that number into this function and calculate. I see that I'm getting a bigger and bigger number. So this process, this limit does not exist. Because when you say the limit exists, it means that the values of the function are gathering around that particular number. Yes? In the previous example, you see, when I am increasing x towards 1, of course they are also increasing, but not that much. They are just being pressed against number 2. Yes? Is that clear here? But that behavior is absent here. If I make this smaller and smaller, this even becomes bigger and bigger and bigger. So it is not getting close to a particular number. In this say, we say the limit does not exist. Yes?
Like what limit was infinite?
No, the limit is still, it does not exist. Okay, let us just go there. The limit does not exist. Yes? But we can say that this is the way that we say it. We say this is plus infinity. It doesn't mean the limit exists. This symbol means this table. This is a behavior process. When you see this, this is conveying this idea to you that the values of the function are getting bigger than any number that you can imagine if you get closer and closer to 0. But it doesn't mean the limit is infinity. Infinity is not a number. Okay, so if you say infinity belongs to the set of real numbers, it is false. Because when infinity is just a symbol that describes the behavior. So it is also, so if I say that I have infinitely many dollars, it's not clear how many dollars I have. Yes? Yeah, so that is important. But if I say I have $1 billion, you will say that he is rich. And if the other person has $2 billion, he is richer. Okay? But if I say I have infinitely, I have infinite dollars, and another person comes in and say I have infinite dollars as well, so and at the end you don't know which one has more. Exactly the same story. N, how many elements are there in N? In the natural numbers, infinitely many. How many elements are in R? Infinitely many. But which one is bigger? It's not that easy. It's possible to answer such a question, but it is not that easy. I want you to understand that. So when you say something is infinitely, it is just a behavior. You are pointing to the behavior of the function. So you ask me a question about a function without any limits. This is one of them. But we had before that we can have, by the way, we can have a very simple function. Let me just write it here. That's a good question. F of x is equal to, let me just write this one for you. X plus 1 if x is greater than or equal to 0, and it is, for example, x minus 2 if x is less than 0. Is that understandable? What does it mean? Forget about limits. Assume that I give you a function. So far you have used to having functions with one rule, but this is a function with two rules. It depends to which input you put in. If you put 0 or larger than 0, the function will obey this rule. If you put a number less than 0, the function obeys this rule. Okay, for example, if I ask you, if I give you this function, by the way, these functions are also in your book. If I ask you f of 1, what is the answer? Because 1 satisfies this condition, it means the function will obey this rule. And it will replace this x with 1. And the answer is 2. Yes? If I write f of 0, 0 also satisfies this rule. So the function will take that rule and replace x there with 0, you get 1. But if I ask what is f of minus 2, what is the answer? Minus 2 satisfies this rule, satisfies this condition. So the function follows this rule and then replace x with minus 2, and the answer becomes minus 4. Yes? Yes?
I have a question about the infinite limit that you talked about before. When you remade the function f of x equals to x squared minus 1 divided by x minus 1 into g of x equals
Yeah, yeah.
is it possible to do that if you have an infinite limit? Like, can you remake it somehow into a new function so that it works in the same way as above? That's what you did above.
I don't exactly understand your question, but if you mean that I can make it, might be I can write x plus 1 over x minus 1, and I ask you to calculate the limit of this when x goes to 1, something like this. Yeah, this is also infinity. So if you get x closer and closer to 1, what happens? The numerator is not negligible. If you are very close to 1, this number is very close to 2, but the denominator is very, very small. So the numerator is something finite, 2. The denominator is very small. You are dividing 2 by a very, very small number. Again, the value of the function becomes huge. Pardon?
Shouldn't it be 1 minus x?
No, it doesn't matter here.
It becomes infinitely smaller.
Yeah. But we have two kinds of infinity. So you brought this up. I wanted to teach systematically because If I put minus, it becomes minus infinity. We have two huge numbers, huge negative number, huge positive number, and then in that case, this one is huge positive, and then this one is huge negative. Yeah. Okay, so I wanted to say something else. Okay, now this is the question. You understand this, but now I ask you the limit. This is interesting. I ask you, what is the limit of f of x when x goes to 0? So this is one, I want you to understand, non-existence of limits is not mysterious at all. So this is a very simple function, by the way, and I am asking you, what is the limit of that function? It does not exist. Why is that?
It depends on which side you're from.
Yes, exactly, because when x goes to 0, one thing is clear. Here is 0. When you see this symbol, means I am around 0, I am close to 0, but I don't know by this symbol if I am a little bit larger than 0 or smaller than 0. Okay? And that is exactly, unfortunately, important because of this function. Because this function splits exactly at 0. So it matters if you're a little bit smaller than 0 or a little bit larger than 0. Okay? So which one I have to use? So even though I ask you to calculate this, you need to calculate this yourself. You need to calculate this limit. You need to calculate this limit and see what happens. Yes? So what is this limit? X approaches 0 from the right-hand side. Which rule of f I have to choose? The first one, because x is a little bit greater than 0. So I have to choose the first rule. Yes? And the answer is 1. But if I ask you to calculate this limit, x goes to 0 from the left, I have to choose the lower one. Do you understand that? Because x is close to 0 but smaller than 0. If x is smaller than 0, I have to choose this rule. And then I calculate this limit. And the answer becomes -2. But then we had this before. If the right limit and the left limit are not equal, what should I say about the limit itself? The limit does not exist. And the limit does not exist is indication of something. And what is that? Discontinuity. It means that the function, if you draw the graph, it will break at the point 0 somewhere. Yes?
So if the function isn't the same, then the limit does not exist.
No, if the limits, the left limit is not equal to the right limit, then the limit itself does not exist. Not because of the function. You don't say this if I ask you how many functions you see here, no, one function. It's one function but obeys two rules. So I am talking about the limit of one single function, not two functions. But depending on the input value, the function obeys different rules. Yes? Yeah. And that is why if I draw the graph of this, let us just draw the graph of it. It is y equals to x plus 1, which is just a straight line. So if you draw y equals to x plus 1, if you draw that one, where is it? It is just here. This is your function. But this is the graph of the whole x plus 1, but you have limited the domain for positive values. So negative values is not acceptable. So it means that from this graph, you have to delete this part, because this part are on the negative side of x. And then you draw another one, which is x minus 2, which is this one. If you draw that, this would be the whole graph. Okay? But this is limited to negative values. So you only consider the negative values. You clean the positive values. Yes? Here, 0 is acceptable, so you have to put a field dot here. But here, 0 is not acceptable, so you put an empty dot here. So if you say, do I have two functions? No, this is one graph of one single function. But this one graph consists of two parts. It is not the graph of two functions. And then you see what is happening exactly at 0. The graph is breaking at that point. So we are losing discontinuity. Okay, but these are not at the, so you're asking, I'm answering, but this is not even in math 4. So the concept of limit is a little bit hard. Okay? I hope that I could answer somehow. So the limit does not exist. By the way, this behavior is not the same as that behavior. If I ask you what is the limit, you should say the limit does not exist. Here, the limit at 0 does not exist. But the behavior of the functions are different. The limit here does not exist because the left and right does not match. Here, the limit does not exist because the values of the function are getting infinitely large. They are not stabilizing around one single point. Yes?
So for that function, if you choose another x approaches some other number, like we say.
Yes, then the limit exists. Yes, exactly. For example, because this is not at the level of your lesson to analytically solve the problem, I always gave you the diagram and ask you the question. For example, I gave you the diagram. I can ask, for example, this is 1. I can ask you what is the limit when x goes to 1. Then you say that, okay, I do it two different ways. When I approach to 1, when I am going to 1 from left, I have this value, this value, this value, and then of course these values are getting close to 2. Yes, but when I also approach from this, I have this value. They are getting smaller and smaller, but still I hope that you agree they are also approaching 2. So the limit of this function when x goes to 1 is 2. Yes? This is the analytic way of doing it. This is graphical way. I want you to understand it graphically. This is at the level of your lesson. But analytically is also algebra is very simple. So I want you, this is not part of your lesson. Okay? Even though I have seen questions in the book, I don't know. Yes, there are some questions of this type in the book as well, but anyway. So is that understandable? Yeah.
I understand the entire process, but how come? Why is it that we can't say that the limit is between the level to the?
No, this is not something we decide. You can come up with it. I want you to understand the whole process of mathematics is like a chess game. You cannot say how it is come that the bishop moves like that. It's exactly the same question that you're asking. Okay, you might say that, okay, I have another idea. If bishop moves like this, then I have a new game. It is more exciting to play. Okay, in mathematics, you should say if you do this, then believe me, this becomes a more powerful tool in your hand. Then if you can convince people, people will actually follow you then. That's what I'm saying. This limit, I am not defining it. I am just telling you how mathematicians have defined this concept. So it means that if you open the book of mathematics and see this symbol there, they mean this. You might criticize why they have defined it in that way. It would be better if they have defined it in this way. It took 150 years to come to this definition. So by trial and error to see which one is more suitable. Yes, that is, I hope that this is the question that you're asking. So you might say that, okay, why we do not say the limit is between this and that? First of all, between this and that, there are infinitely many numbers. Then it is not useful. But then in that case, I say the left limit is one number, the right limit is one number. This is more precise. Because if you have a very broad range of numbers, okay, then what? Yes, that's clearly not very useful. Okay, any other questions? Okay, let me solve one more problem, for example, about this one. So forget about these questions are very good actually. I hope that you understood it a little bit more than the one written in the book. But finally, I want to categorize calculating limits for you to 3 type of problems, yes? One problem of the first type. So what you just put the number there, and you are not facing any problem, so that's the answer. But might be this is not a good. I want you to understand that this is valid argument. Yes. So for this case, if I, for example, here, if x is exactly equal to -1, definitely you get -4. And if x is very close to -1, you get a value very close to -4. In this case, they are the same. And that is an indication of something. It means that if you draw the graph of this function and look at the graph of this function close to -1, you do not see any breaking. Okay, that's the meaning. If the value of the function coincides with the value of the limit, it means that the function at close to that point is continuous. Okay, so the first type of limits is just putting the number facing no problems. That is your answer. These are two examples. Some of them are this type that you have to factorize. So it means that it depends to your skills in factorization mainly. And of course, you factorize, you calculate. So these are two examples on the board. And then we also talked about, but unfortunately, apparently I erased that, yes. We also talked about the surd signs, okay? I gave one example to you, and I want to give another one. So these are three types of problems that you need to know how to calculate their limits. Okay, so let me give you another example. So this is number 6, I suppose. So we want to calculate this limit. Limit of for example, square root of x plus 1 minus 1 in the denominator, x goes to 0, and then in the numerator I put x. So this is again another type of the same type of questions. Yes, we have a surd sign somewhere, and I have problems. Why? Because if I put 0, the numerator becomes 0. So far, that's not a big problem. But when I put 0 in the denominator, square root of 1 minus 1 is also 0. When I say, it's a sloppy language. When I say 0, it means it's infinitesimal, because I am not allowed to put exact 0. Okay, then what I'm supposed to do? I told you just now. The trick is to use the conjugate rule to get rid of the surd sign. Okay, momentarily you cannot get rid of it. Okay, entirely, but you can shift it from numerator to the denominator and from the denominator to the numerator, something like this. So what I'm supposed to do? Do you remember what I told you? You just copy and paste the whole limit again. Everything should be written down. Yes. But then you have to rescale it by some particular, sorry, this is not x, this is 1. By some particular expression. What was that? Can you guess what is that expression here? Yes, Afsha? So just read it for me. No. Plus 1. Because you want to make a conjugate there, yes? And then again, the same thing. So what you have to multiply the numerator and the denominator by is the one x conjugate with the one containing the surd sign. Yes? Is that clear? Okay, and then, so it is better to put pair of brackets around that. And then what you do in the numerator, you just simply multiply. Don't bother to multiply. Just juxtapose them, okay? So just put them next to each other. And then in the denominator, you have to do some calculations. And it is easy. Don't try to multiply, yes? Because you know that this is the conjugate rule, so the answer will be the first one squared, which is x plus 1, minus the second one squared, which is 1. Yes? And x goes to 0. Still, the problem is not solved, because if I put 0, the numerator is still 0. If I put 0, the denominator is still 0. Nothing is cancelled so far. But now this 1 and minus 1 are cancelled, so then I will get the limit x, and then I have square root of x plus 1 divided by x. X goes to 0, yes? Now, what can I do? Still, determinacy is there. Indeterminacy is there. Yes, here, this one and that one are cancelled. Why can I cancel them? Because first of all, they are common factors. Secondly, x approaches 0 means x is not 0. So this is a non-zero factor, even though it is negligible, but no worries, it is not 0. So when I cancel that one, I am left with this expression. Just repeat once more. I am not claiming this function you see here is the same as function you see here, but I am claiming that if x is not equal to 0, the values of this function matches with the corresponding values of this function. Okay? And then if I put x equals to 0, it becomes 2. The limit is 2. Yes, is that clear? Okay. That would be good if you stop here. I will continue one more session with this one because I didn't want to go through these things. I have to introduce this limit a little bit more systematic to you next time, the limit infinity, okay? But the values are infinity. Okay, so I will update the Google Classroom and then you can work on those pages if you want to. No questions? Okay, thank you.
We have a limit that approaches infinity. Are you really allowed to write that the limit is equal to positive or negative infinity?
Yes, because this is the as far as you understand the definition, yes. So it means that, so this is the definition. So if you say, so if I want to say it in words, when you say that the limit, when you say the limit of a function f of x, when x approaches a, is plus infinity, it means that the values of f of x can be made larger than any positive number that you can imagine, provided that you are sufficiently close to a. That's the meaning. Mathematically, it means that for all m, which is positive, there exists a delta which is positive, so that for all x, if the distance between x and a is less than that number, then the value of the function becomes larger than the m that you have already decided about. So that's the meaning. So it means that, and you see this is a universal quantifier. It just tells you for any value, positive value of m, you can make f of x larger than m, but there is one condition that you have to respect. The condition is that make the distance from x to a smaller than a threshold, smaller than a particular value. If it means that if you tell me, can I make f of x larger than 1000, I would say yes, but I have to be close enough to a. Now, if you ask me now, can you make the value of the function larger than 1 billion? I would say still yes, but I have to get closer to the a than before. If you say, can you make it bigger than 1 trillion? And still I would say yes, but I have to get more closer. So this behavior means this. That's it. And then you say that this equality, I understand what is your concern, because we cannot put this sign between a number and this symbol. Yes? But this, what this does, it doesn't hurt. The whole package defined in this way. And then, by the way, in this definition, there is no track of equality sign at all.
No, I guess.
Yeah? So that is just a behavior that you see this. Instead of people writing so many things, they just summarize it like this. Yes?
So the sign itself, like the infinite sign itself, it's just the behavior of something that can go above any number that you can think of.
Yes, mainly this. Okay, but still the concept of infinity is extremely... so for example, if you want, I can give you a very, very surprising example. I was shocked myself when I just read it, okay? So assume that this is the game. I don't know if we have enough time. So assume that you have the balls, 1, 2, 3, etc. You have some marbles numbered 1, 2, 3, etc. But of course, this is not practically possible. Assume that this is the set of all natural numbers. But what you need, that is just n, the set of n. But now take a bag. Let us make it a little bit more exciting. So here it's 11:59 p.m. Okay, like horror movies, yes. And then you are supposed to reach to this time. You have 1 minute. Okay, let us do 2 games. The results are astonishingly different. So you see, when the time is 11:59, what I do, I take the first 10 marbles from 1 to 10, I put it in the bag and throw number 10 away. Okay? So I put number 1 to 10 here and just throw 10 away. Assume that nothing, so there is no time for this process. Of course, this is ridiculous, but assume that. Okay, and then when it reaches to in the middle, I take number 11 to 20, put it in the bag, and throw 20 away. Is that clear? And now, when this is going to the halfway again, I take from 21 to 30 and put it here and throw 30 away. Okay? Of course, you have to do it so fast when it goes getting closer and closer. So I want to divide this interval to halves every time and do the same thing.
So you throw away 1 marble per
Per time, but this number first of all is 10, the second is 20, the third one is 30, and etc. And of course the time doesn't care about what is happening to you, it reaches to 12. My question is that how many marbles will be in the bag? No, let us say which marbles are not there. 10 is not there because I throw it away here.
Yeah.
20 is not there because I throw it away here. 30 is not there because I throw it away when I was here. So it means that all numbers are there except multiples of 10. So how many of them are there? You have the set of natural numbers, take multiple tens away. How many of them are left? Infinitely many.
But there are also
Yes, no, this is not surprising. This is no cheating,
there are also
I promise you, okay?
many multiples of 10. So there's
Yes,
also,
so that's a multiple, so there are no multiples of 10 there.
but there are infinitely many multiples of 10, so we're also missing infinitely many worlds. So
No, you are not, because this is clear. 1 is there, 2 is there, 3 is there, 9 is there.
yeah, but there's also, because if we threw away we have every natural number, right?
Yes,
Which includes every multiple of 10, and there are infinitely many multiples of 10, right?
yes, that's the point. But this is very clear. Even if you take all multiples of 10 away, multiple of 9s are left, multiples of 2. So there are still infinitely many. But look, I changed the game slightly. When I am here, I put 1 up to 10 there, I throw 1 away. Okay? And then when the time reaches here, I put from 11 to 20 there, but I throw 2 away. Okay? And then when I'm here, I put from 21 to 30 there, and I throw 3 away. Every time I put 10 and throw 1 away in both games. Yes? But now the question is that when the time is 12, how many marbles are in the bag? None of them. Yeah, none of them. Because number 1 is not there. Because I threw them away when I was here. Yes? Number 2 is not there. Because I threw it when I was here. Number 3 is not there. Because I threw it away when I was here. Number 4 was not there. Because I threw it away when I was here. So none of the numbers are there by this logic, and that is completely intact logic. So I mean the game, so when it comes to infinities, it is very strange, because it seems intuitively every time I put 10 marbles in the bag and throw 1 away, depending on which I am throwing away, the results are astonishingly different. In the first game, I am left with infinitely many marbles in the bag. In the second case, I am left with nothing.
That's the nature of infinity.
Yes, so that's the nature of infinity was hard. Yes, Ali?
But the the amount of marbles we have in the bag is higher, like 9 times higher than the
No, that's the point.
I mean,
That is not.
The number of even numbers is exactly equal to the number of natural numbers.
That's also why infinity indicates.
So yeah, if I say the number of even numbers matches with the number of odd numbers, you can imagine that's okay. But if I say the number of even numbers is the same as the number of all natural numbers, that's a little bit astonishing. And even if it's more stranger if I say the number of elements in the whole integers, including negative values, is still the same as the number of elements in n. This is even more astonishing. Yes. The reason is that when it comes to infinity, I cannot count. Okay? But how mathematicians try to understand the infinities, that is just the way that illiterate people understand. For example, if you have old times and you have a shepherd who doesn't know how to count, but still he can still understand if a sheep is missing or not, a sheep is missing or not. Because probably they have some woods corresponding to each sheep, and then when sheep are returning back, when the first sheep goes in, he will take one one matchstick and put it next, and then when the second one goes there, he will put another matchstick here. If no matchstick left is in his hand, no sheep are left without matchsticks, mean the numbers are the same. So the shepherd probably doesn't know how to count, but he knows that the numbers are the same or not the same by one-to-one corresponding these two objects. Yes.
But I don't know, or in this example where you remove like one more marble from the bag per iteration.
Yeah.
It feels like, of course, you wouldn't have any left because after like 10 iterations, you would already be removing 10 marbles per time you throw in 10.
So,
I don't see where the surprising part.
No, the surprising part is intuitively, if this is not surprising if I just mentioned that, but from human action point of view, it seems that we are doing the same thing, which shouldn't affect. Because no, look at the problem. I mean that if it's understandable for you, that's okay, because that's the correct way of understanding it. But the point is that for human brain, at least for the first encounter, is that I am putting 10 marbles in a bag. I am throwing one marble out.
Yeah.
Yes? If you think in this way, it's surprising. But of course, logically, it is not surprising. Because the logic tells you that nothing is straight happening. In the first case, multiples of 10s are out. Okay, so it means that there are infinitely many left. But in the second scenario, nothing is there. Yeah, logically it is not, but intuitively it seems a little bit strange in the beginning. Yes? Any questions? So this is why when it comes to concept of infinities, it's a little bit subtle and of course more exciting. But that's not part of your lesson, so you don't need to be worried about it. Learn how to just to calculate limits, okay? Okay, any questions? Thank you.